I'd like to invite all of you to join me today in what I think will be a very remarkable lecture. Um I read about 350 astrophysics papers a week. I don't read every paper completely, but I look at the abstracts and so on. And in the last year, we're going to talk today about what I think is the most exciting of all the papers I've seen in at least a year. And it's new research, so it may be true, it may not be true, but it's so creative and innovative and exciting that I think it's well worth our time. So we're going to talk about biocosmology. So this is, the paper proposes a new science called biocosmology. And the purpose of this new science is to explore the role that life has in the universe, the physical role that life has in the universe. And they claim in these series of papers that they published that the existence of life has changed some of the physical properties of the universe itself in dramatic ways. So let's explore that. Okay, so when I was going to school, when I was Shavam's age, which was just after the invention of fire, this was sort of the view that science had of the universe. There were large things and small things. Particles were the smallest things, and then you got to bigger and bigger things as you moved to the left, and the biggest thing was the universe. And so particles in the universe seemed to be completely unrelated because they were the things that were the most separated on this scale. But we have come to realize during my lifetime that indeed the scale should be more like a circle than a line. And the universe is in fact very closely related to particles, the particles that are in the universe. And both of those have more in common than, for instance, either one has to do with the Earth. So it's more of a circle than a line. And indeed, the condition of the universe determines the abundance of the various types of particles that exist in the universe at any given moment. As the conditions of the universe change, the particles also change, the abundance of the various types of particles. And it's the behavior of those particles that in turn determines the condition of the universe. So this is this yin-yang thing. And this field of study is now called particle cosmology. And that's the field that most interests me. I began as a particle physicist, and we'd never talked about the universe. It was just so immensely larger and seemingly unrelated. But now almost every paper that you read in astrophysics and cosmology begins with a discussion of the particles that they assume exist. Now today we're going to talk about how life changes a property of the universe that's called entropy. And some of you have taken some of my prior seminars, and you know about entropy, but some of you haven't. So I'd like to briefly review some of these concepts. So entropy is a concept within the field of science called thermodynamics. Thermodynamics emerged as the study of heat, particularly to optimize steam engines some 150 years ago. And it deals with gases and pressures and volumes and temperatures and entropy, which are all properties of a collection of particles, a system of which is maybe, for instance, gas composed of molecules, or it could be, the particles could be galaxies within the universe, or the particles could be stars within a galaxy. So by looking at the components of a system, you try to understand the behavior of the system overall. And the science of thermodynamics makes certain critical assumptions about the systems that it's going to describe. So first of all, it assumes that the system has a fixed composition. That means it's always made of the same types of particles. So in a steam engine, you're dealing with gas, and the molecules that are in the gas remain the same types of molecules throughout the entire cycle. You're also dealing with a fixed set of microstates. Now, the microstates are the combinations of the different states that all these particles can have. So one microstate specifies the position and velocity of every molecule or every particle within the system. So it's a complete physical description of the system at that moment. Now, we don't see all of that in the macro world. We see temperature and pressure, which is some average property of these particles. But below that, at a deeper level, there are these microstates. And so when you do thermodynamics, you begin with the particles and the microstates, and you work your way up to understanding pressure, volume, and temperature, and entropy. Another assumption that thermodynamics makes is that the system can pass through all of the different microstates at some point in time. It will pass eventually through every possible microstate, and all these microstates, in a sense, have the same probability that the system is in them at any given time. We also talk in thermodynamics about systems which are at equilibrium or are moving quickly from one equilibrium situation to another. So we're never talking about systems in thermodynamics that are very far from equilibrium. The equations of thermodynamics assume that you have reached some sort of equilibrium condition. And the issue when you try to apply thermodynamics to the universe, when you try to incorporate thermodynamics into cosmology, is that not a single one of these assumptions applies to the universe. So the universe does not have a fixed composition. It does not have a fixed set of microstates. It does not occupy every microstate, and it's never in equilibrium. So we try to apply thermodynamics to understand cosmology, but we have to be very careful because the basic assumptions of thermodynamics are inconsistent with the status of the universe. Now, in thermodynamics, there is this concept of entropy, and I'm going to talk in the next few slides about what that means in a relatively simple point of view. So one of the laws of thermodynamics is that if you move heat from one system to another, or from one part of a body to another part of a body, then you're changing the entropy of both parts, the part you're moving the heat from and the part you're moving the heat to. So entropy is a measure of disorder, as we'll talk about later. And if you add heat to a system, you're going to increase its entropy. If you subtract heat from a system, you will decrease its entropy. And in thermodynamics, we say that the heat always flows from a hot body to a cold body and never vice versa. And in this equation, we have the temperature measured in the Kelvin scale. And the Kelvin scale, just for a brief review, absolute zero is 0 Kelvin, the coldest temperature that anything could possibly be at. It corresponds to minus 270 degrees centigrade or minus 460 degrees Fahrenheit. And you see the temperatures at which water boils and freezes. And the temperature is related in thermodynamics to the average kinetic energy, that's all this stuff, of the individual particles of which the system is comprised. So for instance, if it's a gas of air molecules, then this would be the average kinetic energy of those air molecules. with some constant scaling factor. And just for fun, the lowest temperature that we've ever reached in the laboratory is 38 trillionths of 1 degree Kelvin. So very close, but not zero. Okay, so entropy, as I said, is a quantitative way of measuring the disorder of any system. And that's a complicated statement, so let's see if we can understand what disorder means. A very orderly system is a perfect crystal, for instance, a perfect salt crystal. So you have sodium ions in red and chlorine ions in yellow, and they alternate like a checkerboard. And if it's a perfect crystal, then the locations of all of those atoms are well defined if you know the position of the first two atoms and the angle that you can rotate the crystal at. So there's only these few degrees of freedom. And if you know the position of these two atoms and the rotation angle, then you will immediately be able to calculate the position of every other atom in the crystal. So there is very little information that's necessary to specify the location of every atom because the system is extremely orderly. And that object will have an extremely low entropy. Entropy is denoted by capital S. On the other hand, if you step on this salt crystal and you break it into individual atoms, then you can only know their locations by specifying the location of every individual atom, which is immensely more information than was required to specify the same positions when it was a perfect crystal. So by stepping on the crystal and disassembling it entirely, you have dramatically increased its entropy. You now have a system that is much more disordered, requires much more information to specify than you did before. And there is a theorem, the second law of thermodynamics, that says the amount of disorder in a macroscopic system will always be increasing and can never be decreasing, which turns out to be just a statement of probability. It's much more likely that the system will become less ordered than the probability that it will become more orderly. Okay, so entropy, let me say a few more words about entropy because this is a difficult physical concept to understand. If you have a gas of air molecules, then the macroscopic properties, temperature, pressure, volume, and so forth, don't really depend on what an individual molecule is doing. It depends on what the average of molecules, what is the average of all the velocities, the average of all the temperatures, the momenta of all the particles. So we live in a world in which the molecules are very small compared to us. So we're in the macro world, and we are sensitive to the average properties of the gas, like pressure, temperature, and volume. And we're not sensitive to the actual location of every individual gas molecule. So if you were to swap two gas molecules, you have changed the microscopic state, but you have not changed the macroscopic state. So entropy is the number of ways in which you can rearrange the molecules without changing the pressure, the temperature, or the volume. The number of rearrangements of the microstates that don't change the macro state. And the number of rearrangements is capital omega, and entropy is the natural logarithm with this is Planck's constant. So you multiply by some constant, forget the constant, it's related to the number of microstates. And if you aren't familiar with the natural logarithm, that's the logarithm base e instead of base 10. And if you invert it, this might be more familiar. The number of microstates is the exponential of the entropy divided by Planck's constant. So these two equations say the same thing. If you don't like the natural logarithm and you prefer e, then you're going to relate to this one better than that one, but they're identical equations. Okay, so entropy is a measure of how much microscopic rearrangements you can make to a system without changing its macroscopic properties. Okay, and the important thing about entropy is that in any macroscopic system, which would include anything bigger than atoms, entropy will always be increasing. There will always be an increase in the level of disorder. And eventually, any thermodynamic system will reach equilibrium. So energy will flow from the hot to the cold. The entropy will increase. And eventually, all the pieces of the system, all the gas molecules will have the same average temperature, at which point there will be no further flow of heat because there aren't hot spots and cold spots. They've all come to equilibrium at some average temperature. And at that point, the entropy has reached the maximum possible value that it can have, and there will be no further possibility of any macroscopic changes to the system. So the temperature will be fixed, the pressure will be fixed, the volume will be fixed. Unless there's an external force, the system will be completely unchanged for eternity. And anything that never changes cannot be alive. Life is about change. And so equilibrium is sometimes referred to as the entropy death of that system. Once a system reaches equilibrium, it's finished changing. It's come to the end of its active phase, and it's now going to be unchanging for eternity. And people have talked in the past often about the entropy death of the universe. When will the universe reach a situation in which it's same temperature everywhere and nothing can ever change, and therefore nothing can ever be alive within that universe? This paper that we're talking about today completely contradicts that notion of the entropy death of the universe, which is one of the things that makes it so exciting. So in our universe, we have a system which is not in thermodynamic equilibrium. The universe is continually expanding, increasing its volume, and its temperature is continually dropping. So we don't have a situation in which we're reaching an average equal temperature everywhere. And as the temperature drops, the abundance of the various types of particles change. They go through phase transitions, we call them. So a phase transition is something in which the behavior of the system changes dramatically due to, for instance, a change in temperature. It could be due to something else, but temperature is the most common example. So if you have ice and you increase the temperature, it will eventually melt and become water. And water is very different from ice. Its behavior is very different. If you keep increasing the temperature, the water will eventually boil and evaporate into a gas, which is also very different than water. So the H2O starts out at ice, goes to water, then goes to a gas, a vapor, and each of those transitions occurs at a specific temperature, and it's relatively abrupt. And we call those abrupt transitions a phase transition. And the universe has gone through many phase transitions in its history. And every time a system goes through a phase transition, the microstates of the system change. the number of the various particles change, and so the description of what those particles are doing will be very different than it was before the microstate. And each phase transition increases the maximum possible entropy that the system can have, because it creates new microstates, new ways for the particles to exist. And by creating new ways, the total maximum entropy that the system can have increases. So let's see how that works out. In the history of the universe, from the beginning of time until now, beginning of time on the left, now on the right, it started out early on. It became a gas of particles, and the particles were just flying around at very high temperature. Nothing bigger than a particle existed because the temperature was so high. You might think of this as the gaseous state of the universe. The temperature was so high, then a solid or liquid object could not be formed. Eventually, as the temperature dropped, the particles came together and they formed nuclei, and eventually they formed atoms. And as the temperatures continued to decline, eventually these atoms condensed into stars, and eventually life emerged. So these are several major phase transitions in the history of the universe. And our greatest interest today is this last phase transition with organic material being emerging. So there are many phase transitions in the universe, but let's begin at about 1/1,000,000th of a second and ignore the complicated earlier period. By about 1/1,000,000th of a second, 1 microsecond, the universe was comprised of bosons, the photon, the gluon, and the W and Z bosons. It was also contained quarks, just the up and the down quark. The other 4 quarks had a much shorter lifetime, and it contained the 3 leptons, the electron, the muon, and the 3 types of neutrinos. As the temperature continued to decline, at about 1 microsecond, the 2 quarks, the up and down quarks, were able to coalesce and form larger composite particles like protons and neutrons, and several hundred other more complex composite particles. At about 1 second after the Big Bang, I neglected to say that when these particles existed, the quarks and leptons also contained anti-up quarks, anti-down quarks, anti-electrons, anti-muons, and anti-neutrinos. The bosons are their own antiparticles, but the quarks have uniquely different antiparticles. So at 1 second, the particles and the antiparticles annihilated with one another almost completely, and that produced an enormously large number of particles that eventually decayed, and what was left in the end were an immense number of more photons and neutrinos. By 3 minutes after the Big Bang, protons and neutrons were cool enough that they could coalesce and form the nuclei of the lightest elements in the periodic table. This is deuterium and helium. Deuterium is an isotope of hydrogen that has a proton and a neutron in the nucleus. By about 379,000 years after the Big Bang, the nuclei and the electrons were able to combine at the low temperature that existed then and form neutral atoms. So before, you just had the nuclei and free electrons flying around, and now you had these composite systems with nuclei and a appropriately balancing number of electrons to make neutral atoms. At about 200 million years after the beginning, the first stars formed, and the first stars and all following stars created through the process of nuclear fusion, the heavier atoms. So the atoms of carbon, nitrogen, oxygen, and all the atoms that have greater atomic weights than that, all the way up to iron. The explosion of stars creates the elements after iron. And that came shortly after the first stars. The first stars had very short lifetimes. So when they exploded, then you started to get also elements heavier than iron. And at about 10 billion years, as far as we know, after the Big Bang, was the emergence of the first organic materials, beginning with small organic molecules, growing to larger organic molecules, and eventually to something that we would deem to be alive. So the small molecules are amino acids, the bigger ones are proteins. Proteins are made of many amino acids. It could be 10 or it could be millions of amino acids to make a protein. And proteins are very nice, but we would not consider a protein to be alive. So an individual protein is not alive. We don't have a very clear definition of what life is, but I think we all know it when we see it. As some famous Supreme Court judge said about a different topic. Okay, so let's go back to entropy, the level of disorder. There is, this is in green, the amount of entropy that the universe contained at a given moment in time, starting with the Big Bang and going to today, from the left to the right. And at each phase, between the phase transitions, at each phase, there is some maximum level of entropy that that collection of particles can have. So in the very beginning, when you had a gas of hot particles, they would relatively rapidly come to thermal equilibrium, which is the maximum entropy. So the particles are interacting billions of times a second with one another. The ones that are hotter, higher velocity, transfer energy to the ones that are cooler. And within a relatively short period of time, you reach thermal equilibrium and there's no further change. So this would be an example of the entropy death. At that point, there's no further change until the next phase transition. So at that phase transition, now you have a new set of particles, a new set of microstates, and you have a higher level of maximum entropy. And this situation persisted for seconds, this situation persisted for billions of years, and we never reached the maximum entropy. The universe continued to evolve, continued to change, hot spots continued to transfer energy to cold spots, and we never reached thermal equilibrium, so the universe had not reached entropy death. And with the emergence of life, we have a completely new phenomenon. This entropy limit is increasing exponentially due to the existence of life, and the entropy of the universe is increasing rapidly due to the existence of life, but not nearly as rapidly as the maximum. And so we are in an era in which we will never reach the maximum entropy. And that is a new physical phenomenon that hadn't been previously recognized before these papers.
Robert, could entropy be infinite?
No, not in a finite universe. In an infinite universe, it could be, yes.
Oh, okay.
I don't, I go with the notion the universe is finite, but others disagree. But there, at some point, there isn't much difference between e to the 1 billion and infinity. Mathematically, they're different, but from a physics point of view, they're not that different. Okay, so life is a very different phenomenon than anything else in the universe. And it defies some of the basic principles of physics. So traditionally, physicists have believed, particularly particle physicists like me, have believed that the way to understand any physical entity in the universe is to first understand its particles and what its particles are doing. And if you have a complete understanding of the behavior of its particles, then you can explain the physical entity itself. So if you have two physical entities, the left and right, this one has 3 particles, or the 3 particles represent 3 trillion particles. Here we have 5 trillion particles. And the exercise in physics is to understand the interaction of this particle with this particle, and then the other combinations, organize all that and sum it all up, and you get the interaction of lefts with right. So you put the pieces together and you build up. That's the basic philosophy of Western science. But life doesn't work that way. And this is these are the authors who have written the paper. There are 5 names here. And the one that I recognize immediately is Lee Schmolin, who is one of the most famous cosmologists alive. And he is so innovative and creative and exciting that no one would hire him. He was too weird. He couldn't get a job in the United States. Fortunately, he found a job in Canada. And after 20 years of exemplary work, he was finally offered a job in Pennsylvania. And he goes back and forth between Pennsylvania and Canada. Bad example of American science, the American Institution of Science. Anyway, these authors have written, they claim that they will provide a series of papers which expand on biocosmology. So far, they have written 2. So this is the reference to the first one. The second one is the same thing with the last digit changed. And there will be more, but I don't know when, and I haven't seen them yet. So they say that life is an emergent phenomenon and it is more complex than the sum of its parts, meaning that you can understand all the particles in a human body, but that doesn't let you, that provides no description of why that body is alive. And in fact, if a person dies, the particles are still doing more or less the same thing, but the object isn't alive anymore. And from basic physics, you can't tell the difference because the particle behavior is not appreciably changed. The body might have the same temperature and pressure and all these other things that we can measure, but whether it's alive or not is not something that physicists understand how to discriminate. So we need we need to understand life much better if we're going to try to fit it into the science, physical science. So life is a peculiar example of a field of study from a physics point of view, because the number of possible microstates of any biological system is absolutely immense. It's a phenomenally large number of microstates compared to a non-biological system with the same collection of atoms. And almost none of the various combinations of the microstates that you could, almost none of the rearrangements of a biological system would result in something that's alive. So you can take the DNA of a living organism and you start scrambling the sequence of its amino acids, and you will have the DNA of something that's dead, inert, never been alive. And we can't tell which is which, just looking at the microstates. And almost none of the possible combinations actually exist in the universe because there simply isn't enough, there aren't enough atoms, and there hasn't been enough time in the age of the universe to fill even a small percentage of all the microstates that biological systems have. So this is far and away incompatible with the theories of thermodynamics and other fields of physics. It is remarkably unanalyzable. And biological systems are never near an equilibrium. And in most situations, we find that life grows inexorably to dominate its environment, and it limited only by the available resources, by the amount of carbon atoms and the amount of energy and other things. Life will just expand and consume all of those resources until it runs out of those resources. And there's no way to write a fundamental law of science to say what is alive and what is not alive. And the only driving principle of life is to live, is to be viable. And we can describe nothing more useful than that. We don't have any systematic way of saying what life is or how life will evolve in the future. It's really open-ended because there are so many opportunities for different combinations of the particles of which any living organism is comprised. So these are some of the phase transitions that have occurred on Earth, phase transitions that life has gone through, at least on Earth. So in the beginning, very shortly after the planet Earth was formed, and very shortly after the surface was something other than molten rock, life managed to emerge in a very short period of time. It started with these organic molecules, and then larger organic molecules like amino acids, then even larger organic molecules like proteins. And none of these are things that we would consider alive, but these are the building blocks of life. And then life emerged, initially as single-celled creatures, and billions of years later as multicellular creatures. And we have every expectation that life is continuing to go through, will continue to go through more phase transitions in the future, of which we have no ability to predict what those phase transitions are going to be. But life will find a better way. And it has always in the past, and there's no reason to believe it won't in the future. So let's look at some numbers of what the maximum entropy is, as physicists would describe. And we're assuming that we can use the thermodynamic definition of entropy, even though thermodynamics doesn't completely apply to our universe. And these are the numbers from the research paper that I quoted earlier. Among the particles, the photons, the radiation, photons and neutrinos have the maximum degree of maximum entropy. And that is a number which is 10 to the 90, 10 with 90 zeros, 1 with 90 zeros. And the number of microstates is the exponential of this. So that's a huge number. This 10 to the 90 is more than the entropy of dark matter, more than the entropy of all of the quarks and leptons, protons and neutrons, atoms, and so forth. Those are more like 10 to the 80. So 10 to the 90 is the dominant number. Black holes have higher entropy than anything else. And an estimate of the total entropy of all the black holes in the universe is 10 to the 104. And dark energy has an even larger degree of entropy, 10 to the 122, assuming that dark matter is particulate. We don't have any idea what dark matter is, so there's an assumption there. Okay, so you're in the range of 10 to the 100. All these numbers are in the range of 10 to the 100. I mean, this is 32 zeros more than that, but roughly speaking, they're in the same ballpark. Okay, so these are the numbers we saw before. Now look at these numbers. Dramatically different. This is the entropy of all the pre-life organic material. So the pinnacle of that would have been RNA, short snippets of RNA. RNA is sort of like half a DNA, one strand instead of two. And typically the RNA molecules are much shorter than DNA molecules. They're also very unstable. I think they even dissolve in water. And this was the condition on Earth 3.5 billion years ago, before the emergence of the first life, but after the creation of these organic materials. And you can see now we have jumped more than 100 factors of 10. Just the creation of these organic materials dramatically changed the maximum entropy that life on Earth, that the Earth had. And when life emerged, when the first single cell creatures emerged about 2 billion years ago, this is 10 to the million. I mean, these are phenomenally different numbers than what exists without life. And this was the simplest life. Now we have much more complicated life, so this number is much larger than 1 million. And to answer Jill's question, yes, it's not infinity, but you know, it's close, I guess. I mean, my mathematical friends would chastise me for saying that that's close to infinity, but from a physicist's point of view, it's really close to infinity. Okay, and so the question is often asked, how special is our universe? I talk about that a lot. Sir Roger Penrose, who was the co-worker with Stephen Hawking for much of Hawking's career, and has subsequently won the Nobel Prize. So he is a highly reputable physicist, outstanding physicist from England. He says that our universe is 1 in 10 to the 10 to the 122 power. So here you have the exponent has 122 digits, and then you have to take 10 to that power. So this is some fabulously large number. I don't buy into that large number, but I think our universe is extremely special nonetheless. Now, in accordance with classical physics, classical meaning pre-quantum physics, the equations of motion are exact and they are time symmetric. So that means in principle, you could use the equations of physics to take the current universe and run it back in time and find out what was the initial condition of the universe. There are lots of practical reasons why you really can't do that, but at least in principle, according to classical physics, this is possible. And in fact, it would be relatively straightforward from a theoretical point of view. And so we could find a specific initial state of the universe from which our current universe evolved. There would only be one possibility for the initial state of the universe, given what we see today and the classical equations of physics. And all of the other initial states that the universe could have been in would have evolved into something different. Maybe not very different, but there would be some differences because the equations, the dynamic equations of Newton are exact. So any initial difference would have a different final conclusion. So that's the logic that Sir Roger Penrose uses when he quotes numbers as vast as that. This represents the number of initial conditions in the universe that he believes existed. To give you the paper that I'm describing quotes some various numbers that I'm going to show you here about the extent of life on Earth. There are about 10 billion humans. I think the number is between 7 and 8 billion, but in round numbers, that's 10 to the 10. There are about 10 times as many birds and about 10 times as many trees as birds and about 10 times as many fish as trees and about 1 million times as many insects as fish, and then about 1 billion times more marine bacteria, bacteria in the ocean, than insects on the planet. So this is a lot of humans compared to trees and fish. I mean, not as many, but I mean, we're getting up there. Then in terms of the number of distinct species, it's estimated that there are probably about 10 million different species that now exist on Earth. And scientists probably have documented only about 10% of those. So there are an awful lot of ways that life exists successfully, and life has existed on Earth for over 3 billion years. And it's estimated that of all the species that ever existed on Earth, 99% of them are now extinct. So life is continually evolving and changing its states of existence. And in almost all cases, the states that exist at one moment in time disappear and are replaced by, I guess, better states, or states that are more successful in a Darwinian sense. So life is continually rolling over and developing new and, in some sense, better ways of organizing the resources that life requires. So better ways of utilizing carbon to produce more life and increase entropy, the maximum entropy to the greatest extent, and increase the total entropy, the actual entropy of the universe to the greatest extent. Okay, so the prospects then, the paper says, as long as there are sources of low entropy energy, for instance, starlight is what they focus on most. As long as those sources are available, life will continue to evolve, and there will be continual sequence of new phase transitions, which we cannot predict in any convincing way. And each of these phase transitions will increase the maximum entropy limit of the universe. And they estimate that the availability of starlight will last at least 10,000 billion years. So 10 trillion years. And they get that number from the lifetime of the smallest stars, which are red dwarfs. The smallest stars have the longest lifetimes, the biggest stars have the shortest lifetimes. Now that's what they claim in the paper, and I would modify that even more because life could exist around a supermassive black hole, even in the absence of any starlight. You can extract energy from a supermassive black hole, according to an idea first proposed by Roger Penrose. And life could exist in a stable orbit around a supermassive black hole and extract energy for the entire lifetime of that supermassive black hole. And that lifetime would be at least 10 to the 100 years. This is 10 to the 12 year, 10 to the 13 years. This is 10 to the 100 years. So the age of the universe is 10 to the 10 years. So this is a very, very long time. And there would be no entropy death. Life would just continue. And it continue to evolve, continue to change its formation, and just go on basically for eternity. Okay, so that's all that I had to tell you from the paper. So if you guys have questions, comments, I mean, this is, you know, I find this mind-blowing. So there's got to be something that you guys have to say. This is your chance.
Robert?
Okay, I see Ethan's name up here, so we'll do Ethan and then Jill.
Right, so this kind of is. Oh, I forgot what I was asking. I have to remember it because I forgot what I was asking. So yeah,
I'm sorry, I didn't.
I forgot what I was gonna say.
Okay, we'll get back to you then. Jill.
Ethan, you can interrupt anytime. But my question is, this kind of makes it clear that there is life, but just that we can't imagine what it would be like throughout the universe. Is that correct?
Yeah, right. So there's every reason to believe, according to this paper, and I would concur, that life will evolve. It may evolve in different places beyond Earth, but life will continue to evolve. And we can't imagine what the future of life will be, because it's not something that any of our theories can describe. But life seems to be this force of nature that cannot be suppressed. It overcomes everything. And it overcomes everything because it has the physical property of drastically increasing the microstates. It has so many possibilities that something has to work. Something has to work better than what's working now. There are just so many opportunities that life has that you can't imagine it ending.
Robert, with the effects of global warming and theoretically the 3 tipping points we've just gone through, is there a chance that life, like us human beings, are going to change completely in the next 1,000 years or something here on Earth? Or do you think that we will be pretty much like we are?
Well, evolutionary timescales are more like millions of years than thousands of years.
Okay.
Global warming is a severe change, and the timescale of global warming, the timescale of that change is very abrupt compared to what timescales Earth has gone through in the past, ice ages and so forth. So it's hard to say what will happen, but this is going to be a great stressor on all life on Earth. The abruptness and the severity of the change. And there will be life forms that thrive, and there will be life forms that die out, that become extinct. And, you know, I think humans are intelligent enough to find a way to survive, but there may be organisms that do a better job than we do.
Oh.
Robert,
Yes.
there seems to be a distinct boundary between pre-life and life.
Yes,
Now, question is, what or who gave the breath of life?
yes. I have no,
Can that be answered by purely physics or something else?
there is no scientific answer to what is life, or what gave these organic molecules life. Science has no clue. So obviously, religion does, and that's the answer that most human beings would accept. Um, but if you ask about science per se, science without religion, science can't define what life is and isn't, and science can't uh, explain how life emerged in the first place. I think Darwin does a great job of explaining how life changes from generation to generation, making making the each species more competitive. But Darwin doesn't explain how proteins became alive. And I have never seen a convincing description of that, scientific description of that. And I think the reason is we don't really understand the critical aspect of what life is. Anyway, I don't. I'm sure I don't understand.
Another question, Robert, if you don't mind.
Yes.
Those humongous numbers that they calculated, how were they done? You know, how were they calculated? 10 to the 100,000 or 100 million, those kind of things.
Well, if you want to see some big numbers, you could read my book about life. If you let's take the simplest form of life that scientists have conceived of. So J. Craig Venter, who's the world's leading genomist, wants to build bacteria that eat oil spills and absorb carbon dioxide and other great social benefits. And so he spent many years trying to figure out what was the simplest bacteria that would be alive, that would be able to replicate. Simpler means he could make more tons of this stuff, right? So that was his economic driving force, was to find the simplest bacteria. And he determined that you need 462,000 nucleotide base pairs to form a bacteria that is almost completely self-sufficient. Now, it's called the Minimal Genome Project, and you could Google it. I'm not a biologist, so I can't evaluate the quality of his work, but he's the world's leading genomist, so I presume it's good. Okay, so I use that number, 462,000 nucleotide base pairs makes the simplest life. Now that is, so that's 1 million nucleotides. If you ask yourself, how many different arrangements of those 462,000 nucleotide base pairs are there, then you get a number that has about 200,000 digits. It's 10 to the 200,000. And as far as we know, there's one of those that's alive. Maybe there's 10, but that doesn't matter. There's no difference between 1 and 10 when you're talking about numbers with that many digits. So to come up with a sequence of DNA that's actually alive, that's a miracle. And we have no explanation for how that miracle occurs scientifically, no explanation. There isn't enough there aren't enough atoms in the universe. There isn't enough time since the Big Bang to build every combination of 462,000 nucleotide base pairs. There's not even close. You might be able to build 10 to the 100, but not 10 to the 200,000. So the dramatic question then is, how did we get the right one? Once you get the simplest organism, it can evolve according to Darwin, but you got to get the first one. And that is, I think, the greatest unanswered question in science.
I remembered my question.
Yes, Ethan.
It's really super unrelated, but I watched this video. Apparently, there's a star that's like 14.16 billion or something like that years old, and it's like the scientists are really perplexed about it because what's coming from the star signifies that, and like they researched it a bunch, and yeah, but a bunch of random stuff. But I'll send you the video. I just have to find it.
You know, I discussed that star in a recent seminar. It was discovered this year. And one intriguing aspect of that star, I mean, I think you quoted the age right, is that it's only visible. It was detected by the Hubble Space Telescope, and it's only visible because the light of that star is gravitationally lensed. So
Yeah.
this is, yeah, by a factor of like 10,000. The intensity of light is magnified by a gravitational lens by a factor of 10,000, which is why the Hubble Space Telescope could see it. It's also a very massive and very bright star. I think it's more than 10 times the mass of the sun is what's estimated.
How old is it? Or I mean, how far
Well,
away
it's
is
not
it?
14 billion years old because the universe isn't that old, but
That's what I thought.
it comes from just a few 100 million years after the Big Bang. So it's 13.6 or 13.4 or something like that.
Oh.
It's by far the oldest star that's ever been seen. Now, you know, we could see older galaxies, but to see a single star that far away is really breathtaking.
Okay.
And it has an Irish name, which means morning star. And I don't remember what the name is in the Irish name is, but it means morning star. And morning in this context means the morning of the universe, the beginning of time. This is a star from the earliest period of time. It's a great, it's really a wonderful discovery.
Robert, can you send us information on it
Well, I presented it in one of my most recent lectures.
to our group?
Yeah.
Oh, ooh, sorry about
You weren't doing your homework.
that. Okay, I probably didn't see you.
I will send you some information. I did show the Hubble Space Telescope image.
Thank you. Sorry about that.
It was a recent lecture about something else, and I began the lecture. Oh, maybe that's what. Sometimes you don't get back home in time to see the beginning of the lecture. Maybe that's I give you an excuse. Anyway, I showed it at the beginning of a lecture that was about something else. Anyway, I'm glad you brought that up, Ethan. Any more? Martin, are you coming to California? I guess he's not connected. I see.
When do you think your next class will be?
2 weeks.
Oh, really? You're going to do every 2 weeks for a little while?
Well, in 2 weeks, we're going to do another one of these crazy research papers. I said at the end of the seminar number 42 that that was the last seminar, but two research papers came up that I just couldn't resist talking about. So this is 43, the next one's 44, and that's the end of the seminars. After that, my thought is I will start again with my presentation on Einstein and his theories, Einstein for everyone. And exactly when those will occur, I'll have to figure out. My schedule has been subject to dramatic change as of late for personal reasons. I needed to help my mother, who's 93. And we're moving her from the East Coast to the West Coast and finding her a place. And she's a sculptress, and we have to move her sculptures and on and on and on. So my brother and I have been devoting all of our time to taking care of her, fixing her finances, fixing her living conditions. She needs medical attention.
Wow.
Do you have any books in process that you're actively writing?
Books in process? No, my editor quit. My editor is my wife, and she told me after 52 books, you've had enough.
Everybody's having a hard time getting good employees.
Yes, right. Well, I offered to double her salary, but that wasn't good.
Good thing she has the brains in your family.
Actually, I say I double her salary. She gets all the money. I mean, I never see a paycheck. She's a math major, so she has a degree in math from UCLA. So she rapidly convinced me she could do a better job of managing our money than I could. That took about 4 months of marriage. And since then, I just worry about working and making money, and she somehow manages to cope with the task of spending it.
She just gives you a weekly stipend and that's it, huh?
Well, not even that.
Well, please tell Joan she did a great job on this class.
I shall.
Really,
Actually-
really fascinating class.
Yeah, actually, I say my brother and I are doing all this work to help my mom, but at least half the work is being done by Joan.
Well, you and Joan are angels to do this for you.
Well, it's my mother, right?
Yeah, but you're really angels too.
And she's married to a dysfunctional man who's 94, and I got to take care of him too.
Oh,
That's her second husband, not my dad. And he's really a pain in the neck because, he doesn't want help and he can do it himself. And he keeps his idea of doing it himself of taking care of himself is he only goes to the emergency ward about once a month instead of every day.
I'm told bamboo leaves are really good for people to eat. They're like cyanide.
Bamboo.
Yeah.
Well, I found him a great place to live. I offered to finance it. All he had to do was move out of his house, but he's got 3,000 books and he can't part with any one of them.
Jeez.
Anyway, so we had to go back east and, deal
So
with
you
it.
already went back east and came back
Yeah,
and you
Yeah.
already did the finance stuff?
well, it's a never ending process. They decided they would lock the front door, they would not answer the phone, and they would not open the mail for 3 years.
Jeez.
And somehow they think the IRS didn't notice, and everybody else.
So are you gonna ship all these sculptures and 3,000 books to the West Coast?
No, we're gonna ship a certain number of I told my mother she could have 10 sculptures, not 1,000. She has 61 pieces of art in her living room.
Wow.
5 more rooms, plus a studio, plus a storage unit.
Wow.
How many books are you gonna ship?
Well, those are his books, so he doesn't want to leave the house.
Oh,
But I found a synagogue, and they live in Alexandria, Virginia, and the synagogue of Alexandria, Virginia is delighted to take any number of books on any subject.
Wow.
And then they sell them to support, poor people and whatever. I mean, they have worthy causes. So we're hoping that they will take 3,000 books. He was a geophysicist. So most of his books are science books. Okay, that's the end of my story. Any more questions about today's seminar? I mean, here's a radical idea. You want to talk about today's seminar?
Yes.
Okay.
Yes.
Yes. Okay. So next time in 2 weeks, on the 28th of June, we're going to talk about the second paper that I found very remarkable. And this paper today was published by 5 scientists. The benefit of more than one brain is that when you do something stupid, hopefully the other brain will point that out before you publish. So 5 scientists working together tend to make better work product than one. The paper we're going to talk about in 2 weeks has one author, and he has the remarkable notion that our entire universe is actually the inside of a black hole.
Wow.
And there are parts of the paper that I will critique. I think it's a very creative paper. It's, we ought to think about wild ideas like that, at least some of the time. There are problems with this paper that I'll talk about, but it's a really creative idea and therefore worth discussion.
That's really interesting.
And he actually claims that his theory matches the astrophysical data better than our theory of the Big Bang. But whether or not that's exactly true, I don't know. Okay, so I will see all of you in 2 weeks. And I will also send out to all of you the information that I have about the star that Ethan brought up.
Oh, great. Thank you.
Okay?
thank you.
Great
Thank you,
class.
Robert. And if anybody wants the 3,000 books, let me know. You just have to pay for shipping.
I just want your 52.
Well, that could be arranged. Let's see. Okay. So until next time, bye-bye.
Thank you.
Hi, thanks a lot, Robert.
Yeah.
Thank you.